Today we're looking at modelling motion lesson 2, and that's going to involve differential equations of the form velocity in terms of position, and most importantly, other expressions for acceleration. So we can solve differential equations of velocity in terms of position, and develop and apply other expressions for acceleration. First up is our differential equations of the form v equals fx. Generally, the position, velocity, and acceleration of a body moving in a straight line is given as a function of time. This section considers the velocity in terms of its position. Now, the velocity is given as a function of position, and the position is required as a function of time. We proceed as follows. That is, velocity in terms is a function of position. Now, that means that velocity, which is also known as dx dt, is also a function of x. Now, since v is equal to dx dt, we can then rewrite it as dt over dx equals 1 over fx. Separate the variables, integrate both sides, and in time is going to be the integral of 1 over fx dx. Example 7. Particle moves in a straight line such that its velocity in centimeters per second is given by the following function. We have some initial conditions here. We need to determine the position at 6 seconds. So we need to make a function in terms of time. So rewrite the differential equation. We haven't got a differential equation yet. We replace Vx with dx dt. Now we need to solve this. I need to separate the variables. First, I'm going to flip both sides. So dt over dx would be x plus 2 over 1. Now I can separate the variables, which is to remove this dx, join it with the x plus 2. Hence I can integrate the left-hand side and the right-hand side, which is t equals, and using the power rule, half x squared plus 2x plus c. Now this c value we can work out using these initial conditions. So if we sub in a 0 here and t is 0, we're going to find that c is 0. So using the initial conditions, t is 0 and x is 0, my c is going to be 0, hence my time function in terms of position is the following. What I want to do is try and make x a subject. To do that, I'm going to try and complete the square. First up, I'm going to multiply both sides by 2. So that becomes 2t x squared plus 4x. Now if I want to complete the square, I'm going to halve the 4, which is 2, and then square it, which is 4. So I'm going to add 4 and subtract 4. Hence I've created a perfect square. So I've got this, these three terms becomes x plus squared, subtract 4. I can now add 4 to both sides, take the square root of both sides, and then subtract both sides, subtract 2 from both sides. Now I have x in terms of t. So I can determine the position at 6 seconds by subbing in 6 for t. Subbing that in and evaluating, I get plus or minus 4, take 2 centimeters. Object initially at the origin is moving in a straight line and has a velocity given by Vx equals 2x plus 1 centimeters per second. Calculate the position, velocity at any time t. So we're going to rewrite the left-hand side in terms of time. That is, velocity Vx becomes dx dt. I'm going to flip both sides. So dt over dx equals 1 over 2x plus 1. I'm going to separate the variables. So I'm going to have dt equals dx onto the right hand side, so 1 over 2x plus 1 dx. Now I can integrate the left hand side and the right hand side. In doing so, the left hand side is going to become t. And here, because we have 1 over a function to the power of 1, it's a natural log. So it's 1 over 2, because the derivative of 2x is 2, so we've got to divide by that. So 1 over 2 ln the function plus c. Determine the constant of integration, that is, at time 0, where position was 0. So that means if I sub in that 0, I'm going to have c equaling 0, because the ln of 1 is 0. 0 times a half is 0, so c equals 0. So my function for time is half ln 2x plus 1. Now what I want to do is rearrange and solve for x. So let's multiply both sides by 2. Then we can rewrite this. We can write it e to the power of 2t equals 2x plus 1, and subtract 1 from both sides, and then divide by 2. So x equals e to the 2t take 1 over 2. You could rewrite that by dividing that by 2 and the negative 1 by 2. Now, calculate the velocity of the particle. We're going to now derive this position function in terms of time. So the derivative, dx dt, equals e to the 2t. How? Using our differentiation rules, e to the 2t, the derivative of 2t is 2, multiplied by a half is 1, the power, 2t stays the same, and the derivative of the constant is 0. So now we've worked out velocity and position at time t. You can calculate acceleration by deriving velocity. So the second derivative of position then is 2e to the 2t, and the initial acceleration would be subbing in t equals 0, anything to the power of 0 is 1, so it's 2 centimeters per second squared. Other expressions for acceleration is a big topic in this unit. If the velocity is given as a function of position x, and the acceleration is required as a function of x, we proceed as follows. So acceleration is dv dt. Using the chain rule, dv dt could be written as dv dx times dx dt, because the dx's would cross out. But dx dt is the velocity v, so that dx dt is also v. Hence, acceleration can be written as v dv dx, because that dx dt is the v, and you have a dv dx. So v dv dx. That's on your rule page. This equation for acceleration is used when given acceleration in terms of velocity, such as the second derivative of x equals 4 take v. When you see an acceleration in terms of v, you can use this formula. Because you have acceleration in the variable v, a equals v dv is a suitable choice because it contains dv. Example 9. Velocity of a particle moving in a straight line is given by v equals 16 plus x squared. Determine the acceleration in terms of x. So if we differentiate this function in terms of x, that's dv dx equals 2x. Using the rule a equals v dv dx, we have v, which is up here. We have dv dx, which is here. We can sub those two in. Now we have acceleration in terms of x. You can expand this if you wish. So acceleration equals 32x plus 2x cubed. Example 10. Velocity of a particle moving in a straight line is given by v equals 2 plus natural log of x. Calculate the acceleration in terms of x. Differentiate with respect to x first. So dv dx is going to become 1 over x because the natural log, if we derive that, it's 1 over x. Using the rule, a equals v dv dx. There's my dv dx. And my v was 2 plus ln x. Acceleration in terms of x is simply 2 plus the natural log of x over x. Acceleration of a particle moving in a straight line is given by a, acceleration in terms of v, which is 16 plus v. Its velocity at the origin is 2 meters per second. Calculate the position of the object when its velocity is 6 meters per second. First of all, let's rewrite acceleration is a as v dv dx. I can rearrange by separating the variables. So here, I'm going to divide both sides by v. Now if I flip both sides, which you don't have to do, but it's one way of separating the variables, I flip both sides. Now I'm going to multiply both sides by dv. Now I have a dx on the left and v's and a dv on the right hand side. Hence, I can integrate both sides. Integrating the left is pretty straightforward. It's going to become x. Integrating the right hand side, I'm going to have to rewrite using partial fractions. That right hand side now turns into 1 take 16 over v plus 16, which means I can integrate this because that becomes an x, or v, sorry, and the negative 16 over v plus 16 becomes negative 16 natural log of v plus 16. We have a constant c which we have to work out. And to work out that constant, we need to use the initial values that my position is 0 when my velocity is 2. So sub in a 2 for velocity and a 0 for x, I can work out c. C, in exact form, is 16 natural log of 18 subtract 2. Now I can simplify this expression for position by changing c now to 16 ln 18 take 2. Using some of my logarithm skills, I can write it as v take 2, there's my v take 2 still, but I've got a 16 ln 18 take a 16 natural log of v plus 16. So take means divide, which is why that v plus 16 comes to the bottom, and my numerator is 18. Now determine x when v equals 6 by subbing in a 6 here. And it's approximately 3 decimal places, 0.789 meters. Acceleration given as a function of position. The following relation is used if the acceleration is given as a function of position, x, and the velocity as a function of x is required. To start, we're going to use the chain rule to create an expression for v. Now, ddv of half v squared would be v. So if you derived half v squared, 2 times the half is 1, take 1 off the power. So we create an expression that's formula 1. As seen earlier, equation 2 is a equals v dv dx. Sub 1 into 2 and simplify it. So if I replace that with my v here, and substitute that in, I can now cancel out my dv's and I end up with an expression which is d over dx half v squared. So acceleration equals d dx half v squared. Example 12. The acceleration of an object travelling in a straight line is given by a is a function of x, which is e to the x plus 1 centimeters per second squared. Velocity is initially 1 centimeter per second. Explain why the velocity is always positive. Now, since e to the x is going to be greater than 0 for all values of x, the velocity is always increasing as x increases. If the starting velocity was positive, then it's always positive, which it is. Remember, the initial velocity was positive, so hence that statement is true. Now, to determine the velocity in terms of position, we're going to rewrite acceleration. This ax becomes d dx of half v squared. So e to the x plus 1 equals my new expression for acceleration. I'm now going to rearrange. That is, multiply both sides by dx. Hence, I can integrate both sides. Integrating both sides, my left-hand side becomes half v squared. My right-hand side is still e to the x plus an x plus c. Calculate the constant using the initial values. That is, my velocity was 1 when x was 0. That means we sub in our 0 for x and 1 for v, and c equals negative a half. Solve for velocity. So I've replaced my constant integration with negative a half. We're going to solve for velocity. So v squared, we're going to multiply both sides by 2. Now take the square root of both sides, but v is always, velocity is greater than 1. Therefore, velocity equals the square root of 2e to the x plus 2x, subtract 1. Example 13. The body moves in a line so that its acceleration is 2x plus 1 meters per second squared. When x equals 2, our velocity is 3. Determine v, velocity in terms of position x. So rewrite acceleration. So acceleration is d dx of half v squared equals 2x plus 1. We integrate both sides first by multiplying both sides by dx, then integrate both sides. Our left-hand side will become x squared plus x, and the right-hand side will become half v squared. We can determine that constant of integration, the initial values, which is x equals 2 and v equals 3. We then substitute those values in, and our c value is negative 1.5. So expression v in terms of x is then a half v squared equals x squared plus x take 1.5. Solve for velocity. That's v squared equals, if we double both sides, 2x squared plus 2x take 3. Velocity equals plus or minus the square root of that function. We've solved for v. Example 14. A particle falls from a height of 500 meters above the ground. Calculate the speed of the particle when it hits the ground. Our initial conditions are in terms of velocity and position. Hence, we're going to choose an acceleration equation that involves d dx of half v squared. Acceleration, being gravity, is negative 9.8. And like we did before, let's separate the variables. That is, we're going to multiply both sides by dx. Hence, I can integrate both sides. The integral of negative 9.8 is going to be negative 9.8x, and the integral of the left-hand side is half v squared. Now calculate the constant using the initial values. So x was 500 when it was dropped, so it was initial velocity was 0. We sub in those values and rearrange. C equals 4,900. Next, I'm going to solve velocity. So we're going to multiply both sides by 2, take the square root of both sides. Now I can determine speed as the magnitude of velocity when it reaches a height of 0 meters. So let x, our position, be 0. So I sub in a 0 for x. Then I'm taking the square root of 9,800, which is 98.99 meters per second. We have three different equations for acceleration. The first is d dx half v squared, or we have v dv dx, or the most basic one which we've dealt with a lot is dv dt. So often if you're given acceleration as a function of time, then straight up we just use dv dt. If acceleration is given as a function of velocity, but your initial conditions are in terms of t and v, then use dv dt. If acceleration is in terms of velocity, but your initial conditions are position and velocity, then use your v dv dx. You've got an x and a dx. And here, if you've got acceleration as a function of position, your initial conditions are v and x, then use the following form, which is d dx half v squared. This takes practice, but you'll get used to it after a while. That concludes our second lesson on modelling motion.